Friends, today we will see the next article. Almost it is the last article from our first topic, multiple integral. So it is nothing but Fubini's theorem. This Fubini's theorem will help us to express double integral. Suppose this is the rectangle R. Double integral over a rectangle R of a continuous function as, since you know this is rectangle AB cross CD, R is, here R is AB cross CD. Now, double integral of the function f over a rectangle R can be expressed in terms of limits of x and limits of y. So this Fubini's theorem tells us how to express integral of the continuous function over a rectangle R as repeated integral. Means we are repeating the integrals of this function f of xy dy dx or maybe dx dy. So this is how Fubini's theorem tells us to express double integral of a function f over a rectangle R in terms of repeated integrals, either a to b, c to d, or you may change this c to d, a to b, f of xy dx dy. Okay. Now see what is the statement of this theorem. Suppose f is a continuous function defined on R, rectangle R, which is AB cross CD. Then the double integral of f over R is equal to integral over a to b, c to d, f of xy dy dx, or it can be expressed as integral over c to d, integral over a to b, f dx dy. So this is what the Fubini's theorem is all about. Okay? So we want to prove that integral of f over R can be expressed in terms of this repeated integral. Now see, once again we are doing integral of a continuous function over a rectangle R. Already you know how to define double integral of a function f over a rectangle R. So you have to think two things. First thing is double integral of a continuous function or a closed and bound continuous function defined on a closed and bounded domain, which is a rectangle, and every continuous function defined on a rectangle R is always integrable. So these two things are important, how to define double integral, and every continuous function defined on a rectangle R is integrable. Okay. Now see, to deal with this, first of all we will see the partition of this rectangle A. So suppose P1 as usual is equal to x0, x2, and so on, xi minus 1, xi x1 and so on, say xm or even xl also is equal to b, and P2 is equal to y0, y1, so that yj minus 1, yj, yn is equal to b. Suppose P1 and P2 are the partitions of AB and CD as usual. Then you know P is equal to P1 cross P2. Set up all order pairs of the points of P1 and points of P2, that is xi yj is a partition of the rectangle R, and this, how to partition now this rectangle? So the lines drawn parallel to the coordinate axis, x-axis and y-axis, through the points of P, that is xi yj, will divide the rectangle R into mn subrectangles Rij, which is nothing but actually already you know this thing xi minus xi cross yj minus 1 yj. Where I runs from what we have made, j runs from I runs from 1 to n So this partition P will divide the rectangle R into n sub-rectangles. Okay. Now, as f is continuous, so my assumption is f is continuous. If f is continuous on a rectangle R, then a integral of f over R can be expressed as the repeated integral over a to b and c to d. Now, as f is continuous, already you know, we have proved f is integrable on R. Every continuous function defined on a closed and bounded rectangle is integrable. Okay, so already you know. So therefore, as f is continuous function defined on this, therefore f is integrable on the rectangle R. Therefore, by Riemann criterion, for what is the Riemann criterion for integrability? For any epsilon greater than 0, there exists a partition P of R such that UFP upper sum minus LFP is less than epsilon. Suppose I got this as P equal to number 1. So UFP minus LFP less than epsilon. That is what the Riemann criterion for integrability of a function is. Now, I have dealt with continuity of f and I have this. Now I will define a function, new function a. See, now what I will do is, now I will deal with this part CD. Okay, so define a function a from closed interval CD to R, either from this part to either this part to R or this is also CD, C and D. So I will consider a function now a. Okay, this is function a from CD to R. So define a function from CD to R by a of y is equal to, because we consider that y as the variable from CD, So a of y is equal to integral over a to b f of x comma y dx, and we do this for every y belonging to variable CD. Okay, so for each y we define a function a as a of y is equal to integral over a to b f of x by dx. Now see, this is integral is equal to x. So if you integrate this, as you know, a and b are constant, so this will be a function of, if you put values of suppose 1 to 2, and if you evaluate the integral, answer at the end will be in terms of y. So that is function of y. Okay. Now see, a to b. What is a to b? A to b. So this is a to b, and this is x1, x2, x3, xi minus 1, xi, and this is xn, and so on and so on. So integral over a to b can be expressed as integral over a to x1 plus integral over x1 to x2 plus integral over x1 to x2 to x3 and so on and so. That will be summation of integral xi minus 1 to xi f of x comma y dx. Remember, we integrate this with respect to x, so y is treated as constant, y is fixed. Okay, and I runs from 1 to m. So if you take I is equal to 1, what you get is integral f of x by x0 to x1 plus integral over x1 to x2 plus integral over x2 to x3 and so on and so on. Only integral over a to b is splitted as integral over this to this plus integral over this to this plus integral over this to this and so on, and written as a sum of this. Okay, so here this is my equation number 2. Okay, now again my f is continuous on whole of the rectangle. Therefore f is continuous on AB, and again, and in turn f is continuous on xi minus 1, xi each of the subinterval. F is continuous on both of these, therefore F will be continuous on AB and F will be continuous on xi minus xi minus 1. Thus F is a continuous function. F is a continuous function defined on F is continuous on xi minus 1 xi. Now see here with respect to this 2 or this function, here we integrate this. Now I treat F as a function of x only. That means here x is only variable. So when I treat y as constant, then F will be function of only one variable, and F is continuous on this part where x is variable. Okay, you know every continuous function from fundamental theorem of integral calculus that if F is a continuous function, F is continuous function defined on closed interval AB, then there exists C belonging to either closed interval AB or open interval AB, anything such that f of C is equal to 1 upon b minus a integral a to b f of x dx. That is what the fundamental theorem of integral calculus for one variable is. Now here when I treat y constant, this becomes a function of only one variable. So and as f is continuous on this, okay, so I may write this as, so we will simplify it a little bit, b minus a integral a to b f of x dx. This is what the fundamental theorem or mean value theorem for integral calculus is all about. Okay, so very similar. So I apply now this mean value theorem to this function over xi minus 1 xi. So as f is continuous on this, therefore there exists zi belonging to xi minus 1 xi such that yes, f of zi y, because y is constant, so I will write take forward it as into b minus a. So b minus a, so xi minus 1 is equal to integral xi minus 1 to xi f of xy dx. F of xy dx. Okay, so by mean value theorem, what I have is that exists a point z such that I have this. Therefore, now my ay will become therefore from 2 we have a of y is equal to summation I is equal to 1 here, I is equal to 1 to come f of zi y into xi minus 1. Okay, suppose this is geometry now. Okay, a of y is equal to this. Okay, I have defined a function a from C to R such that a of y is equal to integral of f with respect to x by taking y as constant. For each y, for a fixed y, I have considered this integral of f over a to b. For every y, I have integrated over a to b, and what I have is for this a of y, I have this. Okay. Now consider integral over c to b, integral over a to b, f of xy dx dy. This is equal to, this will be equal to integral over c to b. Now put the value summation integral over a to b is, or I may write this as this is nothing but what is this? This is nothing but a of y, one of this integral is a of y dy. A of y, this is a of y dy, and this is equal to integral over c to d. Now, what is a of y now? Summation I is equal to 1 to m f of zi y xi minus xi minus 1 dy. Again, this is equal to, again what we will do is now c to d, just as we have splitted here a to b and integral over a to b as integral over a to x1 plus integral over x1 to x2 plus integral over x2 to x3. Similarly here we will do for c to d. So this will be summation integral over yj minus 1 to yj, j is equal to 1 to n. This summation as it is f of zi by xi minus 1 and this is dy. Okay, we will write this simplifying. So this is summation over I is equal to I will write j is equal to 1 to n summation. I will write, because integral of sum is sum of integral, so I is equal to 1 to n integral yj minus 1 to yj f of zi by dy. Okay, we will write it properly into xi minus 1, because this is a function of y now, therefore this xi minus 1 is number, it has nothing to do with this. Okay, so now we will try to now simplify this quantity. Okay, now again, as f is continuous on whole of the rectangle, therefore f is continuous on this CD also, and hence f is continuous on yj minus 1 yj also. Okay, so therefore again, as f is continuous on yj minus 1 yj, therefore it is integrable on yj minus 1 yj, and hence by mean value theorem for integral of one variable. So what you have is, yes, f is, right, f is continuous on yj minus 1 yj, therefore so that there exists wj belonging to yj minus 1 yj such that f of zj comma wj. Now tell me, where is zj? Zj belongs to, our zj was from xi minus 1 xi. Zj was here from xi minus 1 xi, and my wj is from yj minus 1 yj. This is the rectangle. Here is, this is yj minus 1 and yj, and this is, here is xi minus 1 and here is xi. So my zj was here, zj is here and wj is here, therefore order pair, this point will be zi comma wj, because here we take suffix as I. So my zi comma wj into yj minus 1 is equal to, so I am applying mean value theorem for a function f by treating x as constant here now with respect to y. So f is continuous on this, therefore just like we have seen, f of, there exists c in between a and b such that f of c is equal to 1 upon b minus a integral a to b f dx or dy. So similarly here, so f of zi wj into this is equal to yj minus 1 yj f of zi by dy. zi by dy. So this is just like a, b, f with respect to y. Okay. So therefore, so my equation 4 now will imply now that yes, how will we know our 4? So this is summation j is equal to 1 to m, summation I is equal to 1 to m. Now this integral is nothing but f of zi wj yj, or I will write this xi minus 1, no problem, because after all now these are the numbers. Okay. Yj minus 1. Okay. So now I have this repeated integral as double summation f of zi wj xi minus 1 into yj minus 1. Okay, I will call it as multiplication by 5. Okay. Now suppose I will take to this side. Now suppose mij is infimum value of f over f of xy such that xy belongs to Rij. Okay, and capital Mij, you know, as usual, this is suppose supremum value of f of xy such that xy belongs to Rij. So let small Mij be the infimum value of f on Rij, and capital Mij be the infimum supremum value of f on Rij. And see, this is any point on this Rij we are considering infimum and supremum, and this is any point here. So therefore, what is the relation between this small Mij and any value of the function? Therefore, small Mij will be less than or equal to value of the function. This is the smallest value, and this is value of the function at any point of Rij. So this will be less than or equal to the largest value Mij. Okay. Now what I will do is, now I will multiply this, each of this by xi minus 1, this factor. I will multiply this and this by this factor, and I will take double summation. Okay, so double summation, I will not write I. Okay, so I will, j is equal to 1 to n mij. This is xi minus 1, xi minus 1 into yj minus 1 less than or equal to again double summation f of zi wj xi minus 1 yj minus 1 again less than or equal to this double summation mij into again xi minus 1 yj minus 1. Okay, now what is this? You know, in double integral of a function, what is this? This is the lower sum of function f with respect to partition p, because these xi and yj they are coming from partition p1 and p2. So this is LFP less than or equal to what is this? From 5, just observe 5. This is the right, this right hand side is nothing but that inequality. So that what you get is integral c to d of integral a to b f of xy dx with respect to 1 and less than or equal to this, nothing but upper sum UFP. Okay. So now from this I will take only one thing that I will require. So from this what I have is LFP less than or equal to integral over c to b of integral over a to b f of xy with respect to the x dy. This implies I will now change the sign. Okay, so I have taken only the left hand side because I require that only. So if I multiply by -1 both sides, then this will change. So minus integral c to b, integral a to b, f of x y dx dy less than or equal to minus lft, right? I have multiplied both sides by -1. Okay. Now again, f is continuous, therefore f is integrable on this, double integrable on. So that means this is the double integral of f over r. And what is double integral of f over r? How we define double integral of f over r? Okay, so it is nothing but the smallest upper sum. This is nothing but the smallest upper sum u of f, or the largest lower sum. Okay, so it is nothing but the smallest upper sum, and here I have any upper sum of the function f with respect to partition p. U f p is also a upper sum, and double integral of f over r is the smallest upper sum. Therefore, this is less than or equal to any upper sum, because it requires this as the smallest upper sum. This as the smallest upper sum. Okay. Therefore, now from these two equations, what I have is now, see, I will consider now double integral over r. Now I will add these two, adding 7 and 6. Add the respective sides. Double integral over r f, okay, f dx dy, or f dA. Dx dy is f dA, or you may write dx dy also. Okay, this minus, because this plus this, so minus sign will come here. C to d. Okay, I will write like this. Integral a to b f of xy dx dy less than or equal to this plus this. So u of ft minus lft. Okay, but from equation 1, uft minus lft, as f is integrable, f is continuous, f is integrable, therefore Riemann criterion, our equation 1 tells us that uft minus lft is less than epsilon. So this is less than epsilon for any partition p. So thus what I have is, I write here only. So thus this is less than epsilon by equation 1. Therefore this minus this is less than epsilon. But what is epsilon? And epsilon greater than is arbitrary. Is arbitrary strong number. Therefore, yes, therefore what we have is this integral f dx dy or dA is equal to integral c to d of integral a to b f of xy dx dy. You may put the bracket or you may not put, it doesn't matter. Okay. So thus what we have to do is double integral of a function f over a rectangle r can be expressed as repeated integral. Double integral can be expressed as repeated integral of f with respect to x and with respect to y. So this is what. Similarly, if we consider instead of considering a function a of y from cd to r, instead of considering a function from cd to r, if you consider a function from ab, either this or this ab to r, if you consider a function b from ab to r defined by b of x is equal to integral over c to d f of xy dy for every x in ab, because my b is now from this to this. Okay, and if you repeat the same procedure for b, what you can prove is integral a to d, integral c to d, f of this is equal to, this integral is equal to f of xy dy dx. So that means integral Fubini's theorem helps us to express double integral of a function over a rectangle r in terms of repeated integral, that's integral c to d, integral a to b, or integral a to b, integral c to d. Okay, so this is how Fubini's theorem is helpful. Thank you very much.